All right, we'll start a discussion in statics about talking about vectors. Okay, and actually, before we get into vectors, let's define what a scalar is. Now, a scalar is just a number. It's a quantity. It has a magnitude, and it's just a number. So 1, 2, 3. So I mean, these are the numbers that we're kind of used to. We call those scalars, and that's again as opposed to a vector, which is not only a number or quantity or a magnitude, but that magnitude, quantity, number, it also has a direction, okay? And that direction is oftentimes shown as an arrow. And we draw the arrow at the length equivalent to its magnitude and at a specific angle relative to some stationary position. Oftentimes it's the horizontal, sometimes it's the vertical, sometimes it might be another vector. So again, the length of this represents how large the number, how big the magnitude is. So if this is 1, okay, this vector drawn here is 1, 2, 3, 4 long. So it has a magnitude of 4 and a direction at 20 degrees, from the horizontal. Okay, and it's heading up and to the right. The arrow shows what direction it's heading in. Okay, now the book, when they represent a variable as a vector, they do it in boldface. So if you're reading the book, anytime you see a bold variable, that's saying it's a vector, meaning it has a magnitude and a direction. When I write things, typically I draw it with a line over the top. Okay, so when working things out on the board, if I draw a line over the top, I'm saying, hey, this is a vector, because it's very hard for me to do boldface on the board. So just keep that in mind. When you see boldface or something with an arrow, it's a vector, meaning it has both a magnitude and a direction. Now, we need to talk a little bit about how we mathematically manipulate these vectors. The first way we're going to talk about is, hey, what if I multiply this vector times a scalar? So again, I have a scalar down here, where I have lowercase a, with no bar over it. That represents a scalar, so that's just a number. Then I have a with a bar over the top saying, hey, this is a vector, okay, so it has both a magnitude and a direction. If I'm going to multiply these two things together, okay, basically the magnitude becomes the two magnitudes multiplied together. So the magnitude of the scalar times the magnitude of the vector, there you go. And the direction is basically the same direction that I had as the direction of A. Okay, we'll talk how we multiply two vectors together a little bit later, okay, because it's a special way to do that. Okay, so for example, if I have vector A shown right here, and I want to double it, I multiply by the scalar 2. Basically, I get a vector that's twice as long in the same direction that A was in. Okay, I didn't change the direction, I just changed the length of it, so it's twice as long now, 2 times A. Okay, say I want to multiply it times negative 1.5. Negative mainly just flips the arrow, so now instead of going up and to the right, I'm going down and to the left. Okay, and the magnitude of this, again, is 1.5 times longer than my original vector over here. I could also divide the same way. If I divide by 2, which is the same as multiplying by 1.5, I get half the size of vector, again, in the same direction. So when I multiply a vector times a scalar, I'm just basically increasing or decreasing the length of the arrow. Okay, I maybe flip, if I put a negative sign, I flip the direction of the arrow. But again, the general angle at which it's going is the same. So that's multiplying scalar times a vector. Again, we'll talk about multiplying two vectors as we move forward. Now, the next thing is we want to talk about vector addition. Okay, and we know how to add scalars. We've been doing that since like the first grade. Okay, but when we add vectors, we have to take into account that that's a magnitude. So if I think about it, I've got two vectors, A and B. Okay, so think about it like giving directions to my house. So I say, hey, you got to go 3 blocks east and then 1 block south. So what I'm saying is vector A is 3 blocks east, right? And then I go 1 block south and I go 1 block south. Now, the resultant vector, okay, which is those two added together, is the direct line from my starting point to my stopping point. So basically I line these vectors up, tip to tail, and I can draw a straight line vector from the start to the stop to get what we call my resultant vector, which is the addition of those two vectors. So again, you go this way some amount, and then you add another vector going that way, and the total amount is like this. Now, when we actually do this, we do it a little bit differently. Rather than using that triangle that I have there, we use a parallelogram, which is essentially the same idea. We start by putting the tails together. So I've got A going off in this direction, B going off in this direction. Okay, everything's starting at the start point. Okay, then I draw these parallel lines, right? So this line right here is parallel to my B vector. This line right here is parallel to my A vector. Okay, and essentially this line is equivalent to my B vector. This line is equivalent to my A vector. I just add them, or I start them in a different spot. Okay, so I draw my parallelogram like that, and then I just sketch the diagonal. That's my resultant. So again, from here, diagonal across to there. Okay, and again, so if you think about it, this is still A plus B equals my resultant vector. Okay. Likewise, I could do B plus A equals the resultant vector. Okay. So just like in math, you know, A plus B is the same as B plus A. Okay. So once I get this, essentially I've got my triangle drawn here. Okay. And I basically go through and I figure out all my magnitudes, all my angles. I'm not going to know some of them, and I use, hopefully you remember this from trigonometry, I use sine or cosine law, okay, where I've got a triangle here, magnitude of the sides, capital A, B, C, with the angles, lowercase a, b, c. Okay. Law of sine follows a relationship like this. Law of cosine follows a relationship like this. Hopefully you remember this, these laws. If not, you know, now you know them. We'll do an example like this in class. So again, you just draw the parallelogram and then use trigonometry and geometry to figure out basically the length and direction of my resultant vector, which is ultimately what I'm looking for. We'll do an example like this in class, but that's how we add vectors, okay, using the parallelogram. Okay, the opposite of this is resolution of vectors. In this sort of thing, we're basically separating a vector into components. So we're starting with my resultant vector. Okay, so I start with this resultant vector, and then what I'm saying is, okay, well, if I'm going to break it up along the a-axis and the b-axis, okay, what do those two things have to be? Or, you know, what are the magnitudes of the vectors in those directions so that I get this resultant vector? So it's doing the opposite of what we just did. Rather than a plus b equals the resultant vector, say, hey, here's the resultant vector. What do A and B have to be to get it equal if I know their directions? Okay, so you start by drawing your resultant vector, okay, and then you basically create a parallelogram based on the axes that you're given. So A-axis, B-axis, and then you draw parallel to the A-axis, parallel to the B-axis. Create your parallelogram, and then you do the same thing, okay. Figure out all the sides that you need to know. Ultimately, what you're looking for, you know, if I look at this triangle right here, I need to know this side, which is my B vector, this side, which is my A vector, you know, parallel to this A vector. Okay, so that's how we do a resolution, just the opposite of addition. Okay, breaking that resultant into components. Again, we'll do a problem like this in class. In this problem, we want to determine the magnitude and the direction of the resultant force. So I have two forces here. F1 is 250 pounds, heading upward at a 30-degree angle from the vertical, and I have F2 of 375 pounds, heading downward 45 angle from the horizontal. Okay, so what I need to do is I need to create my parallelogram. Okay, to do that, I just draw my forces, F1 and F2, and then I draw parallel lines. Okay, so this line is parallel to F1, this line is parallel to F2, and then I draw my resultant force across the diagonal like so. So what I have here is a triangle here that I can then use to solve for that resultant force. So this side of the triangle is F2, so the magnitude of this side is 375. The magnitude of this side of the triangle is 250. Okay. I know that this angle is 75 degrees, and I know that because of the 45-degree angle and the 30-degree angle. So if I had like a vertical line in here, going that way from the vertical line is 45 degrees, alternate interior angles. And then from here to here is 30 degrees because that's the direction of F1. So I know 75 degrees, I know this side is 375, and I know this side is 250. So what I do in order to find the opposite side, I use the law of cosines, which is given here. So it's the square root of each side minus 2 times each side times the cosine of the angle between them. So I have the 250 squared plus 375 squared times 2 times 250 times 3 times 375 times the cosine of 75 degrees. That gives me the length or the magnitude of this side, which is my resultant force, to be 393 pounds. Okay? So that gives me the magnitude that I'm looking for. In order to find the direction, I need to find essentially this angle theta, and then from that I can back out the angle relative to the x-axis. Okay? To do that, I use the law of sines, which is 75 times, sine of 75 divided by the opposite side, or the reciprocal of that. So it's the side divided by the sine of 75 times this side, which is 250, divided by the sine of theta, which is given here. Okay. Solving for theta here, I get 37.89. Now, to put this relative to the x-axis, it's basically going to be, I can use this 45-degree angle to find that, from here to here is going to be 45 plus 37.89, excuse me, and then back out that angle. Okay, they're doing this from the positive x-axis, so it's this whole angle right here. So it's going to be basically 270 plus 45 plus theta gives me that, or as they have it here, 360 minus 45, like that. The other way I could think about this is it's a minus 7 degrees. Okay, so either angle will be fine. It just depends on how you're defining it. Okay, so again, set up your parallelogram, determine all the angles and sides that you know in your triangle, then use the law of sines and cosines to solve the problem. Here, what we want to do is take a force and break it back into its components, okay, or resolve it into components along specific axes. So I'm going to take this 300 Newton force, F1, that's at an angle of 30 from my U-axis, and I'm basically going to break it into a component along the U-axis and a component along the V-axis, and figure out what the magnitude of each of those forces in those directions are. So to do this, I do the reverse of what we did in the other problem, which is I take my force. I still need to draw my parallelogram, but I'm using my resultant effectively this time. So I have to draw that parallelogram. So this line is parallel to the v-axis. This line is parallel to the u-axis. So this time I know my force right here. Okay, I know this angle to be 30. That's given in the problem. Okay. And based on what I have up here, okay, I know that it's 70 degrees between U and V from this angle right here. So that means this angle right here has to be 40, okay? Which means this angle over here has to be 40 from the interior opposite angles. So, and then that makes this angle have to be 110, because 110 plus 30 plus 40 equals 180. Okay, so again, I draw my parallelogram. This time I know the resultant force, and from geometry I can figure out all the angles of my triangle here. So 110, 30, and 40 are my angles, and I know one of the sides. So since I know all of my angles, this time I can use the law of sines to figure out my V force and my U force. Okay, so the law of sines, so I use my U force, which is right here, And I'm going to divide that by the sine of 40, the opposite sign, which is sine of 40. And I'm going to set that equal to the 300 over the sine of 110, which gives me the 205 newtons given here. I do the same thing to find the V side, which is this side of my triangle. So I'll use basically the same equation except the sine of 30 here. So I'll use my unknown force at V divided by the opposite sine angle, which will be the sine of 30, and set that equal to, again, 300 divided by the sine of 110. And that gives me 205 and 160 for those vectors. So again, this is just the opposite of adding them. Draw that parallelogram based on the directions that you're interested in, and then manipulate the triangle using law of sines or cosines or what have you to figure out what the magnitudes in those specific directions actually are.